Okay, next we have Eugene Eagle with Duke Energy and Justin Goodwin with Emerson Fisher Valve. And they're going to give us a case study of some work Emerson did at one of Duke's plants with a new steam-atomized attemperator. So with that, I will turn it over to Justin and Eugene, and they'll introduce themselves and move on. Thank you.
Thank you, Bob. Appreciate the introduction. And so my name is Eugene Eagle. I'm a heat recovery steam generator engineer with Carolinas Natural Gas for Duke Energy. So we cover the Carolinas territory, North and South Carolina, and we have several plants spread across our territory there. Justin, would you introduce yourself?
Yes, sir. I'm Justin Goodwin, Director of the Steam Conditioning Group with Emerson Fisher Valves. My team is responsible for design and support of turbine bypass valves, attemperators, and other desuperheating and steam conditioning equipment. I've been doing this role with Fisher for about 15, 16 years now.
Thanks. Thank you, Justin. So the topic for today is some issues that we've had at Duke Energy with some of our interstage hot reheat attemperators. We've had issues such as overspray, spray to saturation, and some concerns with damage to our Hersig pressure parts and components. So we reached out to Fisher, who was the OEM with the original attemperators, sent them some operational data, and they were able to come up with a solution to this concern with HRSG damage. So that's the topic of this presentation. So initially we started out at one of our units and we worked with Fisher to come up with a field trial to install their design. And it was actually a retrofit installation, which really cut down on the initial cost. And we were able to reuse the existing Attemperator spray ring and some of the initial setup as far as the steam pipe and the liner and some of those components that we didn't have to replace. So I'll get into the history and the background of why we needed a design change, and then of course I'll turn it over to Justin from there to get into some of the design and operation of attemperators. And then I'll close it out with some data and some information and how this has improved our temperation. So a little bit of history and background. Like many of you, we're operating more flexibly. We've kind of transitioned from base load operations to more low load turn down. A lot of this is driven by renewables, increase in renewables. And we're having to do a lot more cycling of our units, like many of you are having to do now because of the increase in renewables. And if you look at this this chart, this displayed in the presentation, these the three lines, the red line, the white line, and the pink line, those are all the attemperators, or excuse me, the thermocouples downstream of the hot reheat attemperator. And two of those lines you can see are going down to saturation, which is the darker line. And you can see the response. That's clear evidence that those thermocouples are getting wetted. You see the jagged lines, they're not smooth and straight. So two of those three thermocouples were going to saturation, getting completely wetted with the Attemperator spray. And so that's definitely a cause of concern anytime you see that in your plant operating data. This was happening during low GT loads. At that point, you have less steam flow. Your steam's at lower pressures. You're not getting the steam velocities that you would at full base load. And so we were getting a lot of unevaporated spray going downstream past our elbow and quenching these downstream thermocouples. So this is a ring style attemperator originally with, I believe originally we had 4 spray nozzles, the spring loaded just kind of standard spray nozzles that you see in a lot of these Attemperator systems. And so that's a little bit of, if you'll go to the next slide, Justin. So at all these units where we're having these issues with overspray, they are the GE 7FA combustion turbines. With those, we see the very high temperatures at these part load operations. I think they call it the 1200 degree isotherm. For us, it was between about 40 and 160 megawatts. And we would see exhaust gas temperatures from that CT get up to 1185 degrees. Now at Buck, we were able to reduce that down to 1170 by making a few tweaks. So that did help us a bit, but we were still seeing this overspray to saturation. And there's a sister site called Dan River where they were also having the same issue. They did not make that adjustment with the CT exhaust gas temperature. And in addition to the very high exhaust gas temperatures at these low loads, the design of the unit itself exacerbated the issue. We had a very large amount of heat transfer surface downstream of your point of injection into your steam pipe. So in this particular unit, you had reheater 4, and then it would go into reheater 3, and then from there, the steam flow split off into reheater 1 and 2. So as you can imagine, there's a lot of heat input that this Attemperator has to overcome in order to maintain those reheat steam temperatures going to your steam turbine at the set point of 1050. Both of these units were built just about 10 years ago in 2011 and 2012. And as I was saying earlier, we were concerned with some potential damage downstream at the elbow downstream, also some of our lateral connections, potential for some uneven heating and quenching of those pressure parts leading to cracking. And we do have periodic high energy piping inspections that are completed. And one of those inspections revealed we would expect a through wall crack, or I think a crack initiation in approximately 4.7 years of continued service. So that certainly was a concern, and that drove the need to find some solutions. Next slide. So this is just a left-hand side view of the heat recovery steam generator and the hot reheat Attemperator location, and you can see where the steam pipe comes down the side of the unit roughly 25 or 30 feet after exiting reheater number 4. And where the red arrow is pointing, that's the spray injection point for the reheat Attemperator spray nozzles. It continues to go up in a vertical configuration, and the downstream elbow is approximately 21 feet from the spray injection point. Okay, next slide. So this is a kind of a closer view of that steam pipe where the spray injection point is there at section B, view B. And it shows the downstream elbow. And one interesting difference between these two sister sites, Buck and Dan River, is that at Dan River, those 3 thermocouples downstream of the Attemperator was just after this elbow, whereas Buck, you had another, I'd say 15 to 20 feet even further downstream of that elbow, and that's where those thermocouples were located. It's a little bit of a difference, and that's a key point for some of the plots I'll show you here a little bit later on. Additionally, we also mounted some thermocouples at the elbow to monitor for differences in the intradose and extradose, and also 4 thermocouples just downstream of the internal liner on the steam pipe. We mounted those externally to look for impingement of spray water on the steam pipe and to help calculate some of the stress and damage to that steam pipe. So I just wanted to point out the layout of the steam piping at these 2 particular sites. Okay, next slide, please.
All right.
Okay.
Thanks, Eugene.
Thank
so I'm going to take a few slides to just kind of catch everyone up on the operation of the traditional mechanically atomized nozzles that are normally used in these ring-style Attemperators. These are spring-loaded nozzles to provide increased rangeability and back pressure to the spray water control valve, allow you to operate at lower flows without losing the pressure drop you need at those nozzles. So the way they operate is they kind of fluid exits the nozzle as a sheet, or in these types of nozzles, it's a cone shape, which breaks into ligaments and then into droplets here. And so I provided a general image of how these work, and then some pictures that show how these things actually work in operation. So you can see the cone here. This is a spring-loaded nozzle. The bottom is a lower tier fixed orifice nozzle, but just gives you some of the images of you can see the sheet, you can see the ring or the ligaments that it breaks into, and then the droplets as those inertial forces pull that outward. So, just basic mechanical nozzle breakup. And then I don't talk about the idea of secondary atomization, but you also get some breakup through the reheat steam, in this case, in our topic here, the velocity of that steam based on its density and based on the temperature of the water and its velocity, you get some additional benefits. But but there are limits to these types of nozzles. They do, of course, require a specific minimum water pressure drop to atomize the water, and that varies by manufacturer and nozzle size and capacity and things like that. But they rely on the water pressure to create the spray. Over time, these nozzles, depending on the material, you may get sticking due to oxidation or sticking due to clogging, a buildup of particulate. Typically they have relatively small passages that if strainers are not effective enough, you can get some plugging of them. This image on the right here is a spring-loaded nozzle that had been filled with little just chunks of particulate. So instead of a nice cone of spray, you're getting a whole bunch of jets coming out of that nozzle because it's plugged up. That can kill your rangeability, and of course your droplets get very large because instead of spray, you're getting a bunch of small water guns, if you will, pointed at your piping. So definitely can be problematic if you get these things plugged up. But if they stick also due to oxidation, for example, they'll stick wide open or closed, and that will, if it's closed, you just won't get the spray you need. If it's open, it kills your rangeability because the spring loaded portion of it really becomes ineffective. Then over time, any damage to the sharp edges at the exits of the nozzle can increase your droplet sizes and decrease uniformity just as they wear over time. And so that will reduce the atomization performance, which is why we generally recommend inspection and replacement of the nozzles on certain intervals just to maintain optimal performance. But as Eugene was saying, we're starting to find operating scenarios that may also require smaller droplets than even a clean, correctly sized nozzle can generate. Particularly these operation with low steam flows and high water requirements that he was describing. So I'm just to show you some fun pictures here of so a nozzle. Again, this is a fixed orifice nozzle that I hope no one would ever install in a reheat Attemperator. This would be a terrible idea due to rangeability, but it really makes the point of what happens to a nozzle as you decrease the pressure drop. And really that's by decreasing the spray flow, assuming constant conditions on the steam and water side. So what starts out as a relatively good spray, although nothing like what you'd want to put in an Attemperator, starts to collapse on you as you decrease the flow further and further until eventually the surface tension in this particular nozzle can overcome the inertial force trying to break it apart, and it just collapses on itself. Now again, no spring-loaded nozzle would hopefully do this, but this still shows what can happen just in general on mechanical atomized nozzles. As you decrease your pressure drop, you are decreasing the atomization, even if you're using a spring-loaded nozzle that has a minimum operating flow. And so I threw in an extra picture of a spring-loaded nozzle operating below its min operating range. It still can come down to a point where the needs of your system start to decrease below what that nozzle can do. Now, ideally, when the product is sized and selected, you'd never get yourself in this situation, but we know over time the needs of the system have evolved, and if that sizing hasn't been relooked at, this kind of problem can exist. I do sometimes get the question, well, what's the shutoff class of these nozzles? Well, they're not intended shutoff. We're relying on the spray water valve and the block valve, ideally the block valve, to get you that shutoff. So if those are leaking, the water is going to come out the nozzle. It's not providing additional shutoff. So this is the kind of leak by that it might look like if you've got a really poorly closing spray water system. So that was just the introduction to mechanical, so that we can kind of contrast that with the idea of steam-atomized water injection. So the idea of steam-atomized water injection basically uses a high-pressure steam source as the mechanism to generate the spray, instead of relying on the water pressure drop in the nozzle. So you inject water into a high-velocity steam flow, which really just shatters that water into a really fine spray. Just can give you a fog-like mist that's much more readily absorbed into the steam. And I noted here an important characteristic of steam atomization is generating fine droplets regardless of water flow, regardless of water pressure drop, or the flowing velocity in the steam. You know, at low flows in a traditional nozzle, if you have high enough steam velocity, or perhaps you've designed your liner in such a way as to drive those velocities up, you get this secondary atomization effect. But as the steam velocities drop off further, you lose the ability for the steam to do enough work on those droplets to continue to break them down beyond what the nozzle itself has done. So that's called secondary atomization. And this steam-atomized design really doesn't rely on that. So if you get to low enough flows or low enough steam densities, which also affect that secondary atomization, the steam-atomized design can still give you that really fine spray. This is an example of a steam-atomized design here, the Fisher DSA desuperheater. The challenge with a product like that is lots of weld joints, probe style thing. It's really not the ideal product for an Attemperator. So we didn't want to try to put that in this. It just wouldn't survive this environment. It's intended for paper mills and things with low pressure steam lines that need a lot of water injection. So after these conversations with Eugene early on, when he was describing the challenges they were seeing at Buck under these low load scenarios where they were trying to turn the plant down overnight instead of shutting it off, and we were seeing these diverging thermocouples, we undertook a project to try to find a way to improve that system. And we wanted to design a steam-atomized nozzle that we could retrofit into the Fisher ring style Attemperators that they had installed at Buck station. So one of the big design objectives is we didn't want any weld joints, shrink fits, threads, or anything within the nozzle itself to ensure long life in this kind of Attemperator environment. Surely all users have seen failures of Attemperators, especially probe style Attemperators. And so we needed a nozzle that could withstand the thermal shocks common in these type of Attemperators that tend to turn on and off commonly. So I wanted to make sure that we eliminated those joints that would be the high risk areas. We did want to be able to retrofit into that design, fit in existing, what we call the nozzle bodies, which are these injection points. And then for new installations, you know, decrease the downstream pipe length requirements and increase rangeability, because we know that's where the industry is going as the CT technology is evolving. So far the Attemperator technology had not been in, so we needed to make a step change and catch up with what the plants needed. So the resulting design here, solution came through additive manufacturing. So Emerson's utilizing laser powder bed fusion, which is basically a process of laying down a layer of powder and then laser welding that together, and then another and another to 3D print these nozzles. You can see what our final design iteration looked like here. So the additive manufacturing eliminates all the weld joints inside the nozzle where we would have the highest stress, thermal stresses due to operation. So this is a design that we patented, and an image here of some of those nozzles that we printed, and these nozzles went into Buck Station. So this is a print bed, and then the rods are the test pieces, because this is basically, you consider this a heat of material. So we have to do the mechanical tests on every heat that we produce. So show you an image here our lab demonstration, our lab testing, as we tested several iterations of this nozzle. And this is really some of the most telling of the wonders of steam atomization. So hopefully this comes through clear through a WebEx, but you can see there's just a fog coming out, and look at the bottom right here. As we turn it off, the spray just kind of dissipates into the air. You don't see droplets falling. There's nothing that continues to fall out. Gravity hardly can act on the size of these nozzles because they're so fine. So it just disappears into a cloud in the air as we turn off the water and the atomizing steam. So that's what we retrofitted into Buck Station. And in a few minutes, Eugene's going to show some of the benefits there to his system. But as far as other benefits of steam-atomized attemperators in general, and in this way, is we really eliminate, the thermal shock failures of probe styles. There's well known in the industry that kind of some all-in-one temperators often don't survive this, particularly those that have trim down in the hot stream. So this can eliminate those types of things. Highly resistant to plugging. I talked about small flow passages in the traditional spring-loaded nozzles. These have much larger flow passages. They don't require small passages or sharp edges to create a fine spray. Much larger flow passages than in traditional nozzles. We completely eliminate the two most common failure modes of spring-loaded nozzles and attemperators. There's no moving parts to stick open or closed, and no springs to weaken or relax over time that can change your rangeability. They're highly corrosion resistant. I know we and other attemperator manufacturers offer upgraded materials to spring-loaded nozzles, from like a 400 series stainless to some sort of nickel alloy. That's a common upgrade. These are in line with the high nickel alloys as far as corrosion resistance. Not a concern. And the same simple maintenance that comes with a spring-loaded nozzle. Just unbolt the flange, pull out the nozzle, and drop in a new one with new gaskets. So simple maintenance, no additional complexities that come with that. So I'll hand it back to Eugene, who's going to kind of talk about some of the issues they've seen and the solutions that we're showing up here.
Okay, very good. Thank you, Justin. And I would add that every 2 years is our recommended interval for going in and removing our spring-loaded nozzles and testing them. We have a test rig at each site where we'll spray and make sure it has the proper pattern. You're not getting that nozzle to stick or the spring to break. So that's one of the benefits of this new system, is we won't have to go in and do that testing. We're still getting an understanding of how often we'll need to replace these nozzles, and we're working with Fisher on that. But so far, we think at least 3 years, or probably more than that. But we've been doing some testing of those nozzles at different intervals to see if there's any erosion or wear, and so far there really hasn't been any. So still working with Fisher to understand those replacement intervals. So as I had mentioned earlier, so we did an initial field trial on one of our units. We were really pleased with the results of that installation and how well it was working. It really pretty much eliminated the spray to saturation issue. So from there, we installed it at the other unit at that same plant. Then moving forward, the sister site, we installed this steam atomizing system on both of those units. So that was 4 units. And then here recently, last fall, we discovered what you can see in these photos. So this is a hot reheat attemperator. And the first photo there to the left is the liner itself at the edge of the liner furthest away from the attemperator. And you can see the cracks starting to develop there in the liner. Also on the other unit at this particular site, there was cracks developing just downstream of the spray nozzles in the liner. Pretty severe cracking where we're concerned about this liner starting to break apart. Additionally, at the same site, the first weld downstream of the liner that you'll see in the next photo was developing cracks in the weld itself. And that was where you saw that view in that second photo on the previous slide, was where we actually had to cut out a section of reheat steam piping to replace that weld because the crack was actually extending into the base metal. This is an older site. It was constructed or went commercial in 2002. Initially, it had the Culp's Vulcan Attemperator a little bit further downstream. And I think around 2003 or 2004, we did a retrofit under warranty and upgraded to a ring style Attemperator, which you saw in that photo. This cracking was discovered this past fall, so we know we're having some issues with some overspray, maybe some leaking block valves, putting some water in that pipe, causing some pretty severe cracking. When we did the NDE on this crack, they measured the depth at 0.685, and this is a 1-inch thick pipe, so that did cause some concern that this crack was starting to go through wall and could be a potential safety concern. So we did initiate projects to move forward and install this steam atomizing Attemperator system at these two units as well at the Smith plant. So that's what these photos are showing, as some of that crack. And the second photo there was a bore scope that I performed on the system and found that initial crack at that bottom weld of that steam pipe. Additionally, there is some cracking that's starting to form at the elbow immediately downstream. I don't have pictures of it, but it's just something we're monitoring. It's at the center of the it'd be the center of the extra dose where that water is impinging on the pipe. So you're getting some unevaporated spray that's contacting that extra dose of that elbow, and it is causing some cracking that we're currently monitoring. Next slide. So this was the initial drawing for the field trial and a couple of photos. Of course, with a steam atomizing Attemperator, you have to have a higher source of steam to create this pressure drop to atomize that incoming spray water. So for us, we were able to use our HP system, and we tapped in to the steam coming out of the HP drum. That provided the pressure needed, and the temperature was low enough where we could use carbon steel to kind of minimize some of those project costs. And that's one thing to keep in mind. This will only work for your hot reheat system because you do have to have that higher source of steam. So you wouldn't be able to install this type of system for an HP Attemperator. So you can see where we had a couple of isolation valves, and then the steam line went roughly 90 feet to where that reheat Attemperator was located. We had a steam pressure control valve, a couple of downstream isolations, and because this was a retrofit, we did have to install a relief valve, and that was because the original Attemperator was not rated for your HP, HP system pressure. So therefore, we had the pressure reducing valve and then a relief valve, and then the connection to the new steam atomizing spray nozzles. And there was 2 nozzles instead of the original 4. We did have to also upgrade the temperature control valve for a larger rangeability. And there were a few lessons learned from this initial field trial that we incorporated on the projects going forward. And the first was that connection. We did a 1-inch to a 2-inch connection. So we did increase that because that's a bit of a choke point for the steam flow. And also that pressure control valve, we did add a couple of pressure transmitters downstream to better control the pressure that the reheat Attemperator was seeing. And then a third lesson learned is that we used Y valves, which have a larger pressure drop. So that was probably a poor choice of valve. We should have used a ball valve that would have a 4-pound differential pressure drop versus about a 20-pound using those Y valves. So those were some of the lessons learned from that initial installation and a couple photos. All right, next slide. So this was one of the sites where we installed the system, the before, and then once again, you see those 3 thermocouples that are downstream of the Attemperator, a very jagged response indicating those thermocouples were getting wetted. And so 2 of the 3 were going to saturation. And the way these are installed, they're at different angles into the steam pipe, and typically the one at the top would stay well above saturation, and the two that were closer to the bottom of that pipe, or the gravity would kind of take hold of that on an evaporated spray flow, those would go to saturation, and that's what you're seeing there in that plot. And this, like I was saying earlier, this happens at those low CT loads. In this particular case, looks like we're about 135 megawatts. CT exhaust gas temperature was around 1183 degrees, and you can see spray flow is very high, around 40 or 42 kilopounds per hour. So a lot of spray flow at these conditions, very challenging given the low steam flows and steam velocities. Next slide. So this was the after plot, and so I tried to pick some similar operating conditions. I think at this point we're at 125 megawatts of CT output, similar CT exhaust gas temperature of 1181 degrees. And you can see those three thermocouples, no spray to saturation. The lines are very smooth. You don't see a lot of that oscillation, plenty of margin to saturation. You do still see a bit of a spread, and you have to remember those thermocouples are immediately downstream of the elbow here at Dan River, which is a little bit different than the plots you'll see next. So a lot of improvement in the system. You're still getting a little bit of cooler steam contact one of those thermocouples, so it's not all completely uniform, but you're not getting that overspray to saturation, which is a huge improvement, and we feel that will buy us a lot of time in protecting the Hershig pressure parts. Next slide. So this was a plot showing those thermocouples I mentioned that we installed on the steam piping, and this was the before the steam atomizing Attemperator was installed. So this is the original spring-loaded nozzles. The thing that I was kind of keyed in on this plot was the difference in temperature between the outer elbow, which is the darker blue, and then the inner elbow, which is the green color. And you can see when that outer elbow gets quenched because of all that and I can't speak today. The unevaporated spray that's going to the outside of the elbow just from the force of taking that turn. So you see that outer elbow go to saturation, and the inner elbow is hanging up there around 700 degrees or so. So you got about a 300 degree differential across that elbow. And of course, once you go to low load, as you can see from that top blue line, the temperatures get a little bit closer together because you're just spraying so much in, but you are getting these pretty large differentials in temperature, so that causes some concern. Unfortunately, I don't have a good plot for the after for those thermocouples, and the reason is those when we did our HEP inspections, those thermocouples got damaged, and we haven't reattached them yet. But what I have seen is much more uniform temperatures on these thermocouples at some of the sites where they're still installed. All right, next slide. So this is Buck, and very similar. You see those three thermocouples, and these are the ones that are much further downstream, as shown in that, I think, slide 3 or 4. And you can see all three of those thermocouples right there at saturation, and we're at low loads. Can you close the door, please? Thank you. And so, yeah, once again, the CT is at a low load of around 106 megawatts. All right, next slide. And this was the after plot, and you can see plenty of margin of saturation. All three thermocouples are uniform, no large oscillations in the temperature output, so indicating no wetting of those thermocouples. So much improvement there after the steam atomizing Attemperator was installed. Next slide. And just another view. So typically during startup was a time where we would see these thermocouples go into saturation. You think about you're moving through some very low loads as you're bringing the HRSG units up. And so that was another time that was very challenging for attemperation during that initial spray and maintaining your reheat steam temperatures. Often we would see those thermocouples go to saturation. So this is a startup after the system was installed, and you can see how well those 3 outlet thermocouples are staying together, and plenty of margin of saturation once again. Next slide. So this was just an overview of the 3 sites and kind of where we're at. So we did that initial field trial in 2019 after we worked with Fisher and got a project to install that first system. And since we were pleased with it, we did the modifications on the other unit at Buck. That was in 2020.
Pointed out 12 lies that the former president told.
And then at Dan River, we completed the installation on both units and here recently in spring of 2021. And then this fourth quarter of 2021, we have the projects planned at Smith. So that was all I had. I'll just say that we have been pleased with the system, and we appreciate working with Fisher to provide a solution to this challenging condition. And I really feel like it'll certainly help our units in the future going forward. And one thing I did want to point out is that the design of the logic is very important with these systems, because you always want to have the steam flow before you initiate any spray flow, because the one concern we had would be any kind of water flow without the atomizing steam. You could certainly cause some issues and some damage. So we have some excellent support from Emerson and Fisher, and we have some good internal talent to develop some of that control logic for these new systems. And that's all I had. This last slide there, Justin.
Yep, thanks, Eugene. Yeah, so we'll take questions. I think Barry's going to moderate that, but certainly we learned a lot. And Emerson also working with Eugene on this. What aspects were important? What parts of the system had the biggest impact? We made, like you said, a few modifications based on our lessons learned, and it was a really good project for us, and I feel like we are pushing things forward. So thanks for your time too, Eugene, and thanks everybody for your time.
Thank you, Eugene. And Justin, I'll handle the questions on this one. First question is from Coleman. I've only got the one name, so I'm not sure what the Coleman. Can you unmute yourself and ask your questions?
Yeah, this is Patrick Coleman. I was just curious, and I apologize if I missed it. What's the most number of hours you've had on a single set of these nozzles, and what have your inspection results been? And then I was also curious if you guys have seen with the new nozzles, any of the spray patterns kind of laying over on the liner next to where that nozzle penetrates. And I think you mentioned it in some you've seen on some other older units or some older installations, I guess.
Yes, if you can recall that one photo, I don't know, Justin, if you want to cue up the photo. I think it was slide maybe 18 or 19.
That one.
And like you said, yeah, you can see that patterns on the steam pipe where that spray flow is contacting that internal liner. I have performed a bore scope since we've installed these steam atomizing nozzles, and I can't specifically recall seeing those, that same spray pattern. The color of the pipe, had kind of that whitish texture, but yeah, I'd have to look back at the bore scope photos, but I don't specifically recall seeing that same sort of pattern where you get your spray impingement on the pipe. And then the other part of your question, I believe, was related to how many hours in service. So yeah, at Buck, we did the initial field trial in the spring of 2019, and those units are around 85 to 90% capacity factors. So they pretty much run, other than planned outages, they're pretty much online, and maybe a few weekend shutdowns here and there. So a lot of hours on those nozzles. We did remove the initial set of nozzles in the fall of 2019 after about 6 months of operation. And we visually inspected them. Really didn't see any significant erosion at all or any changes in that nozzle. And then we sent them off to Fisher, and they did some further X-ray examinations and some destructive testing. And Justin could probably speak to their results better than I could.
Yeah, so we've done that twice now. We did one after a short 6-month install time, and then we installed another set of nozzles for I think the next 18 months. Eugene, you can confirm me on that. And then both times we pulled those nozzles and we did X-rays, and we sectioned them and did surface examination looking for any kind of crack initiation, and found nothing in the nozzles at that point. So the longest service life of nozzles that we have been able to destructively test has been 18 months. And like Eugene said, they're running pretty constantly during that time. And it looks like the same types of ups and downs as far as GT load, if I understand that correctly, Eugene, during that time as they were operating before, where they were seeing these issues. So does that answer the question?
Yes, thank you.
Okay, the next question is from Charles Turner. Charles, you want to unmute and ask your question?
Yes, excellent presentation. Quick question. There's been, the legacy logic for interstage for attemperators has been to have the block valve closed during non-attemperated operation and then open once you get above a certain percentage of required control valve output. But there's been changes that have been recommended lately, and that's to have the block valve open even during a non-attemperated operation. But the concern has always been the leak by of a closed control valve, and especially with insertion type 1, there's a drain or a ring type. The springs don't all, so you could have this introduction of extremely low, just a stream coming in. But it looks as if this could, this steam atomization, if it was on during this kind of period, could alleviate a lot of those concerns about a stream coming in and either distorting or impacting the liner or even just streaming downstream to the elbow. Just a comment on the logic and the application.
Yeah, so I would say, first of all, one, as far as atomizing a stream, if that atomizing steam is flowing, your water flow, I mean, even leakage flow through the spray water system would be atomized, unlike in any other Attemperator system, because it doesn't matter how little water flow there is, as long as you have atomizing steam flow, that will break up that water. I'm not sure I caught if there was another piece of that question that you were looking for. Maybe I missed it.
I think the question was with the, there's been a lot of pipe damage due to a Attemperator leaking when the boiler's off and hot or at very low steam flows when you don't want the Attemperator in service. So the most recent thinking and recommendations is to always, one, have a good quality, good condition block valve, and then open it once on startup, leave it open to avoid wear and tear, so that when you do get to the shutdown condition, you can trust the block valve to be tight and avoid the leakage related damage. So Charles' question is, all right, so you're running, generally it would be at high loads when the Attemperator would come out of service during normal operation. So you've got very high steam flow through the pipe. And if the question is, if you have some leakage water dribbling in because control valve's leaking, is that going to have negative consequences to the pipe? Or will that high steam flow, keep that water entrained and evaporate it?
So the atomizing steam certainly would do that, as long as you have that atomizing steam line open. If you don't, and you've closed both the water and the atomizing steam, but you're getting water leak by, I would say your risks of that water impinging are similar as a traditional attemperator. You need the atomizing steam flowing to get the spray flow to get the spray, the atomization.
Charles, I think I don't personally know of any cases where this change of the logic has caused cracking due to this dribbling water not being picked up. However, some clients have chosen to install 2 block valves. Metal seated ball valves are not that expensive in this big scheme of things. So a good number of people are specifying new construction and retrofitting 2 ball valves in tandem. One of them operates the way you described, where it opens and closes once during startup and once during shutdown. The second ball valve is then allowed to operate in concert with the control valve to eliminate the problem you described. So not to hijack this into something else, but go ahead.
Yeah, that's correct. And you know, the double valve with a telltale leak detection has been another recommendation. It's just cost, and this could be a. Go ahead.
No, you go ahead. I'm sorry.
That's the I just have clients that when you do discuss the change in Attemperator block valve logic, they are very concerned about the potential for this. It's good to hear that from a user's perspective that there hasn't been a documented case where the change in logic has produced a downstream effect.
Well, realize when I say that, that's just what I'm aware of, and that's not any database of significant size that you could count on it. But the second block valve is a pretty good idea. I'm seeing that on a lot of new construction, frankly.
Yes.
A couple of points I wanted to add was, we are concerned because we do have a single block valve on these units, and we are concerned with the leak by, putting water in the system without the steam atomizing steam being emitted. So one of the things we're doing is actually adding an ultrasonic flow meter to every one of these units that have this system. That way it can quickly detect if you start to see changes in the water flow with the block valve closed, and then as soon as possible we'll get the block valve replaced. So that's going to be a fleet standard for us going forward and give us that quick determination that block valve is degraded, and then we'll replace it with a full metal seated severe service block valve like Bob mentioned. And let's see, another point I wanted to bring up was the control logic. We've made a lot of improvements at our sites because oftentimes you'll see that block valve cycle thousands of times, over a certain period of time. So it's cycling a lot more than it should. So we've adjusted our control logic to try to keep that block valve open for longer periods of time and not go through so many cycles, which certainly can cause seat wear and damage leading to leak by. So those are a couple of improvements we've made.
Thanks. Thank you, Charles. Pam Chelvin, you want to unmute and ask your question?
Yes, sir. I have 2 questions. The first one is, can this Steam-Atomized Attemperator be used in the hot reheat bypass line? The second question is, when you come up for the steam pressure and temperature parameters, for example, in the conventional boiler system where they have these low NOx burners firing number 6 oil or number 4 oil, they use steam-atomized guns. And so they do this spray flow, spray characterization, like the droplet size, the spray pattern, all those items to get an optimum spray characteristics for that application. Do you need to do such a spray characterization for this water Attemperator using steam to come up with the optimum pressure and temperature that's available upstream? Or you didn't do that, or you just come up with some kind of a pressure temperature which holds your turned on water flow ratio for different loads?
Yeah, good question. So we did a bunch of lab testing and analysis to come up with some parameters based on the amount of water flow and the pressure drops and how much steam flow we needed, and actually learned through our field trial at Duke Energy some areas to optimize that, particularly for these reheat Attemperators and what's happening in those steam pipes. So I would say we set some internal parameters for ourselves that we would consider confidential at this point on how to set those parameters for atomization. And then your first question, what was your first question again?
Can this be used in the hot reheat bypass line?
Yeah, the idea of steam atomization certainly can. And we've so far developed capacity ranges up through what we would commonly expect to see in reheat Attemperators. You know, reheat bypass valves have a magnitude more water flow required than an Attemperator. And so it's a different animal, but the concept of steam atomization certainly is still applicable, and nozzles like this could be used in that application as well.
Thank you.
Thank you. Joe Schroeder, you want to unmute and ask your questions, please? Joe? Okay, I'll read Joe's questions. Joe's first question is, how much steam flow is required?
So we have some target percentages of steam flow by mass of the water that we have used as a starting point, and then dialing in pressure drops. So we've been in the range of 15 to 20% by mass of the water flow, and then on top of the flow amount, you know, really the critical piece is the delta P of atomizing steam at the injection point, because you want to create a critical pressure drop so you have the highest possible velocities of steam right at the point of water injection. So it's kind of the combination of those two things that have given us the optimal atomization parameters.
Okay. Joe's second question is, are there any potential problems with wet steam causing problems with valves and piping at the letdown?
Yeah, we've kind of been monitoring that together. And Eugene, do you have any insight into, have you seen any damage in the atomizing steam piping to date? Because we were concerned about it at the nozzle, certainly, and that's why we've been inspecting for erosion and have not seen that at the nozzle. But have you seen it in any valving yet?
No, not to date. There was a couple of things I wanted to mention to this point. So the first is this latest installation we're doing at the Smith station. We're going to put automated drain valves. One of the main reasons is because the steam supply line is a little bit longer, because that hot reheat Attemperator is actually at the bottom of the unit. So you're going all the way from the top to where the steam drum's at, all the way to the bottom. So, you know, there is a bit of a concern with maybe some condensation in that supply line. So we want to be able to remove that on startup. The second point I was going to say is, you don't need a temperation until you're much higher in load. We don't typically need it until you're above maybe 40 to 50 megawatts during your startup, because at that point, that's when your CT exhaust gas temperatures get a lot higher, and your steam temperatures follow those exhaust gas temperatures. By the time you're at that point in load during a typical startup, you know, your steam drum pressures are already high enough and your temperatures are high enough where you're not going to see the wet steam. You know, you have good quality steam at that point. So we haven't seen any issues in that regard.
Thank you. G. Martin, can you unmute and ask your question? I think this is another email address, so I don't really know what his name is.
Hello, can you hear me?
Yes.
Okay. Yeah, that's me. Sorry. My question is regarding the nozzle. When you built it, it was through additive manufacturing. What kind of spec do you use to build it? What I mean is international spec or to actually manufacture it?
Yeah,
That
so
was,
so the material of the nozzle is looking for the right slide here. Maybe I don't have it listed here, but it's a cobalt chrome alloy that's a defined material grade. I think within ASTM, and so I'm not sure maybe how to answer your question, but it's not a material that we are having to self-certify. This was an available material for has an added manufacturing grade. These are being produced at R31233 cobalt chrome alloy. So it's a hardened material, not that dissimilar to alloy 6, cobalt based. So very erosion resistant to wear resistant as well.
okay, thank you very much.
You had a second question, didn't you, about percentage of water?
I did, but it was answered a couple minutes earlier. I was asking what percentage of atomization steam was used or is used, and he actually answered it on the previous question. He said it was between 50 and 25% by mass. Right. So someone else beat me to it. Thank you.
All right, thank you. Tanya Craddock, can you unmute and ask your question? Okay, I'll read the question.
Oh, sorry.
Go ahead.
I was just wondering if you all replaced the control valves or block valves whenever you did any of the projects, or was it just liners and nozzles?
We did replace the water temperature control valve, but not the block valve. So the water temperature control valve did require a larger, I think, rangeability, and Justin could probably elaborate on that. So the TCV for the water flow was replaced. And so, did want to reemphasize that the first 2 sites at Buck and Dana River, those were retrofits, and the last site that we're installing this will be a complete new replacement of the Attemperator. And we're going to do the same thing. We'll replace the temperature control valve for the water spray flow only. The block valves were recently replaced at that last site at Smith. So we feel like we'll have good isolation for a while. And then we're going to upgrade to the flow meters to monitor for any leak by. The original flow meters, the DP transmitters, they don't seem to be nearly as reliable, especially for those low flows. And so it's a lot more difficult to detect any leak by using those installed flow meters. Justin, did you want to elaborate on the TCV?
On the TCV, so I would say one of the big things is we kind of started fresh with the sizing and selection. So instead of relying on the original, I believe these were Vogt-Hersig sizing parameters, we did a in-depth dive of some historian data that Eugene provided, and all the way down to whatever the minimum water flows that we needed, and then up to the max range. So that significantly broadened our needs for water, and so that dialed in the valve sizing. The other impact to this type of design is, since it's not a spring-loaded nozzle, you do have to be more careful with back pressure, because it's the exit is a fixed orifice at the water side, so that we have to size around that. So that broadened the needs for the spray water control valve rangeability.
And that's an important point, that you want to use operating data instead of trying to rely on initial design data, because you might have had a CT upgrade or other design changes that could have an impact. So it's very important to use your latest operational data.
Yeah, or just simply the addition of trying to run at low loads in the evenings or overnight. That was not in the original design intent, and so that made some changes to the operation as well.
Good point.
Thank you.
Okay, I have a final question here about, is it applicable for high pressure final stage Attemperator? And I think the answer is going to be no, right?
Right. So
because you don't have a steam source.
You don't have a higher pressure steam source. So this is confined to reheat and lower pressure systems in general, because you got to have a higher pressure steam source. But in our experience, what we've seen is that there are more issues with the reheat steam line than there are in the HP systems. And part of that is just evidence-based and reporting-based, but scientifically, if you look at the water droplet breakup coming out of an Attemperator, again, that what we refer to as secondary atomization, the breakup of those droplets due to the steam line and not by the nozzle in any Attemperator, is based on steam velocities, water temperature, and steam density are the big factors. And so the HP line has much higher steam density than the reheat line. So it's acting on those droplets much more heavily than the reheat system is. So typically it is able to break up those droplets further in even a low load situation where your water pressure drop may not provide the most ideal droplet sizes in a historical nozzle. The steam itself will evaporate the water quickly and break up the water more quickly than it would in a reheat system. So I would say both of those things point to the reheat being the bigger target and, of course, the only place we can really apply this type of technology.
Okay. Barry, I understand you've got a couple of more questions there that came to you.
I have, if there aren't any more important ones, I have a couple of chemistry questions. I know you don't want those, but I thought that might be interesting. So
well, go ahead.
Justin and Eugene, I wondered whether you had seen any electrostatic charges associated with these Attemperators.
Eugene, you want to take that?
That's the first one for me. I don't know what to look for.
Okay, so when you form droplets, there's an electrostatic charge that's associated with those. Every steam turbine on Earth has this enormous electrostatic charge, and so you've answered the question. But I wondered whether any of these units also had been using film-forming substances, because film-forming substances affect the surface tension, and the droplet formation is a function of the surface tension, obviously. And so I wondered whether you had seen anything. We see if we add film-forming substances to plants that we monitor, then we see a change in efficiency because it changes the nucleation event of droplets, which is basically the same thing that you're dealing with here. So I guess the blank look indicates that you haven't looked at these things, but they just seem to me that they might be interesting here.
Yeah, we don't use film forming products in our combined cycle units. We're on standard ABTO with
Good.
phosphate in the
Good.
HP and IP drums. So.
Yeah, because you would take reheat Attemperation right from the right from the peak, where on a unit that would have film forming substance, right from the boiler feed pump section on the boiler feed pump probably, and that would be right directly applicable to quite a high concentration. So Justin, that's maybe something that you can look at some of your other plants if you're doing this at other plants.
Okay.
Justin, nobody gets out of here without a chemistry assignment.
Yeah, apparently. I should know Barry by now well enough to know that.
All right, I've got one more question that was previously submitted, and it has to do with actually it's two questions with the pipe lengths. One was, how do you calculate the pipe lengths for this different than you would normally? And the other is, how does the minimum pipe length to the first downstream elbow change when you move from a conventional nozzle to this nozzle?
Yeah, great question. So I would say, first of all, how does it change? So smaller droplets are always going to shorten your pipe lengths as a general rule, because smaller droplets evaporate much faster, much higher surface area of the water and all those things. In general, we've had steam-atomized desuperheaters for a long time. We just haven't tried to apply those in a Attemperator due to expected life. And so we had a good basis of background, both empirical and calculation evidence of these things. So in general, there's a lot of things that go into downstream lengths, water temperature, percentage of water versus the steam you're injecting it into, things like that, how much superheat you have left, all those things. But as a general rule, I guess I would generalize it as in the neighborhood of 30 to 40% reduction in downstream length, broadly, all kinds of exceptions. But it's a significant reduction. And so for new plants where you're trying to really shorten that downstream distance, this is certainly a good option to try to do that. And then what was the other half of your question?
Say again.
And then was the other half of your question?
Well, I think you answered it with that.
Okay, good.
There was one final question around maintenance intervals, which you guys spoke to that, but if you could recap what you think the maintenance interval will be for this system.
Yeah, so I'll give my answer, and Eugene, feel free to jump in and add any comments you have. In our analysis of these nozzles, actually the slide I have up is a convenient location for us here because we've eliminated several of the failure modes of spring-loaded nozzles here. Sticking nozzles, failed springs, and plugging of nozzles. So I would say the expected failure mode of these eventually would be a thermal fatigue failure internal to the nozzle, which is why every time we've extracted one, we have sectioned, we've done RT and sectioned them and looked for crack initiation because we want to make sure we've done CFD and FEA simulations of the nozzles under conditions that Eugene supplied to us and trying to understand how many cycles each nozzle should be able to stand. And it came to a number of several thousand thermal cycles from extreme sitting at the reheat steam temperature and sudden injection of water. And so the maintenance intervals are going to be longer than any spring-loaded nozzle because you've eliminated several of the failure modes, and we'll be kind of supplying recommended maintenance intervals on a case-by-case basis based on how the unit is being operated and what the operating conditions are. Eugene, anything to add to that?
As far as replacement intervals, right now we're still trying to determine that. I think conservatively, we're going to take maybe a 3-year replacement interval until we build more confidence and understand the longevity, just based on some of this destructive testing and analysis, sending the nozzles out, as well as we have, like Justin said, we've supplied data to try to look at the number of times it goes through a thermal cycle. So that's something I think we still are working with Fisher to determine a lifetime for these nozzles and a longevity.
How about in general, are you keeping to the same intervals for inspection of liner and so forth? Or are you backing off of that as well?
Yes, so I will continue to perform a bore scope of the internal liner every 2 years. That's just kind of our fleet standard, as far as looking at the liner and then trying to get to the elbow downstream and looking at the welds in the elbow internally. Then, of course, we'll continue with our high energy piping inspections, and they typically it might be a 4 to 5 year interval that we're stripping insulation and performing inspections of the welds using linear phased array to look for cracks of the welds. We'll continue to do those sorts of inspections, until something drives a change to those.
Right.
Until we have more confidence.